Okay, hi everyone. Can you hear me?
Yes.
Okay, great. I had problems logging in this morning. Um, that's why we're running late. Okay. Right. I'm going to. Oops. Share my screen. Okay. There we go. Okay, I'm going to share my screen in just a moment here. Okay, still waiting for PowerPoint to load up. Back to Zoom. And okay. Okay, as soon as PowerPoint loads, we'll get started here. All right, here we go. And there we go. Okay. Okay, and okay, sharing my screen. Okay, looks like we're not waiting on anyone else. Okay, in this chapter, we've looked at the properties of alkyl halides or haloalkanes, and we've also looked at two of the dominant mechanisms, both substitution. Okay, so this is the general reaction for substitution. Okay, we have some nucleophile, some electron pair donor, displaces a halide ion, and we end up with a product that has the same bond order. So there's all single bonds in the starting material and in the product. Okay, the halide is referred to as the leaving group. It's what gets kicked out. This alkyl halide that we started with is known as the substrate. So the nucleophile attacks the substrate, we get a product, and we get a leaving group. Okay, once again, these are just a few of the substitution reactions that we can do. This is a very useful mechanism. Alkyl halides are very useful starting materials because we can convert them into so many other starting material, other products, I should say. Okay, for example, alcohols, we can make ethers, we can make thiols, sulfides. We can make iodides from chlorides or bromides. We can make amines or ammonium salts. Okay, and we looked at two variations of the nucleophilic substitution reaction. They were called the SN2 and the SN1. S stands for substitution. N stands for nucleophilic, and 2 means it's bimolecular. There's two molecules involved in the transition state. Turns out it's also second order kinetically. Okay, so this is the general way in which an SN2 reaction occurs. Okay, this is also an introduction to arrow pushing. We show the movement of electrons, not atoms, when we push arrows. The backside of the carbon here is electron deficient. It's partially positive. And so the nucleophile has a high electron charge density. So it attacks the backside, and at the same time, it pushes out the bromide. Okay, so there's a bond formed and a bond broken in the same step at the same time. So this is the transition state. Okay, this is where we get the 2 from. Transition state is made up of both the bromomethane and the hydroxide. There's a bond being formed and a bond being broken. Then it goes on to products. Okay, I also want to reemphasize that the configuration at the carbon is inverted. Okay, in bromomethane, you wouldn't be able to tell, but if this was a stereocenter, we would see complete inversion. Okay, it's just a one-step reaction. There's no intermediate. All right, in the SN1, there's 2 steps. There's a sequential rather than a simultaneous making and breaking and making of bonds. Okay, the first step involves complete ionization. Okay, with terbutyl bromide, bromide leaves, giving a carbocation intermediate. In the second step, the nucleophile attacks the carbocation. If this carbocation resulted from a chiral center, okay, the carbocation is no longer chiral because it's planar. the nucleophile could attack from either side, and we would get a racemic mixture. Okay, we would get equal amounts of both enantiomers. Okay, so here, methanol is probably the solvent, and it's also the nucleophile. So there's a large excess of it. So it attacks. There's a bond formed between oxygen and carbon. The hydrogen here is still attached. All right, so another methanol comes along and it pulls this off, pulls off the hydrogen, this pair of electrons, then moves on to the oxygen. So this bonding pair now becomes this non-bonding pair. All right, since oxygen gained a bond, it now carries a plus charge. Okay, so if the nucleophile is neutral, then there is an additional step in which a proton is taken away. All right, there's two steps in an SN1. There's a reactive intermediate. Okay, the first step is the slow step, the rate determining step. Okay, once this carbocation is formed, then the nucleophile attacks it very rapidly. So this is the fast step. Okay, and because the first step, the ionization, is the slow rate determining step, the nucleophile is not involved in the rate law. Rearrangement can occur if we can obtain a more stable carbocation. Okay, so make sure that you work through the pushing electrons workbook. That will give you exercises on how to do rearrangements, how to do arrow pushing. Okay, so in this example, when ionization occurs, we get a secondary carbocation, which then rearranges to a tertiary. And it does that by a methyl shift. Okay, here is an example of where we do have a stereo center. Okay, we saw this last time. I'm going to go through it fairly quickly, but we have a stereo center. This is the R enantiomer. And once the chloride leaves, this is now achiral. And so the nucleophile could attack from either side. So we'll get both the R and the S products. Right, in the SN2, the nucleophile strength is very important because the nucleophile actually pushes out the leaving group. In an SN1, it's not so important because it's not involved in the rate determining step. And so you could use a weak nucleophile like water. Okay, so here's a list of nucleophiles. We have the good or strong nucleophiles up at the top. Weak nucleophiles, water, alcohols, carboxylic acids. Those are poor nucleophiles, and then these in the middle are moderate. Okay, so the stronger the nucleophile, the faster the reaction in an SN2. SN1 reactions are governed mainly by electronic factors. That is, number one factor is the stability of the carbocation that's formed. Okay, so if we have a tertiary carbocation being formed, then it's then SN1 is likely. If the substrate is methyl or primary, then it can undergo SN1 because the carbocation is way too unstable. Okay, secondary halides could go either way. Tertiary halides like tert-butyl bromide are too crowded on the backside. The nucleophile can't get into the backside, so So we can't do SN2. Okay, bromoethane, on the other hand, has an unhindered backside. So the nucleophile can come right in and push out the bromine. Leaving groups. Leaving groups can affect, can and do affect the rates of both types of mechanisms. Since in both cases the leaving group leaves in the rate determining step. In the case of SN2, there's just one step. Iodide is a very good leaving group. Turns out it's also a good nucleophile. Iodide, bromine, chloride, these are good leaving groups. Water is a fairly good leaving group. OH is a very poor leaving group. NH2 minus is even worse. Okay, so the greater the stability of the leaving group, the faster the reaction. All right, in the Organic 1 lab, we're doing an experiment similar to this next week. We're doing an SN1. It actually will be tert-butyl alcohol, so there we won't have this extra carbon here, but it's the same mechanism. Okay, so sodium chloride won't do anything because OH is a really poor leaving group. Okay, so we're going to take this tertiary alcohol and react it with concentrated hydrochloric acid. Okay, the first step is protonation of the oxygen. Oxygen picks up a hydrogen. And then water leaves. Water is a much better leaving group. We get our carbocation, and then the chloride attacks. Okay, water can also come back, so this step is reversible. Okay, so we're converting hydroxide into water as the leaving group. Okay, for an SN1, it's better if you have a protic solvent. These are examples of protic solvents. They have an OH group, so they can solvate or surround both cations and anions. Water is a particularly good polar protic solvent, but your halide may not dissolve all that well in water, so you may want to use methanol or formic acid as your solvent, for example, methanol or ethanol. Okay, so these will promote the SN1 because they facilitate the separation of ions. Aprotic solvents are better for SN2. Okay, these will solvate cations but not anions. And so the anions are not bound. They're not bound by solvent molecules, and so they can more freely attack. We can do many SN2 reactions in a protic solvent, but typically they're going to undergo reactions faster than an aprotic solvent. Okay, these are examples of aprotic solvents: dimethyl sulfoxide or DMSO, acetone, dichloromethane, ether. Okay, so this is where we left off. I think it was useful to review some of the important concepts here. Okay, we want to look at several things. So the question is, okay, there are several things that this is asking, but let's determine first whether it's SN1 or SN2, which one is more likely. Okay, we want to look at the substrate, whether it's methyl, primary, secondary, or tertiary. We want to look at the solvent. We want to look at the nucleophile. Okay, so for number one, what class of substrate is that? Is it primary, secondary, or tertiary? Okay, you can answer on Zoom also. The primary, secondary, or tertiary? It is secondary, yeah. Okay, so 2-chlorobutane secondary. Methanol is a nucleophile. Is that a strong or a weak nucleophile? Okay, you got a 50-50 chance on this one. It's weak. Okay, it's weak nucleophile, secondary halide. Okay, methanol is also the solvent. Is that a protic or aprotic? It's protic, okay. Okay, so secondary could go either way, SN1 or SN2, but we've got some other factors. We've got a weak nucleophile, we've got a protic solvent, okay? And so which one of the mechanisms is more likely? Okay, secondary halide, weak nucleophile, protic solvent. Okay, is it SN1 or SN2? SN1 is correct, yes. Okay. All right, so the mechanism, let me zoom in just a little bit here. Whoops, too far. Okay. And zoom in a little bit more. All right. Okay, so we said this was SN1. Oops. Looks like I'm off screen. Okay. SN1. Okay, so the first step is the chloride will leave. Okay, there's a hydrogen going back here that's implied. Okay, so chloride would leave. We would get a carbocation and a chloride ion. And our solvent and our nucleophile is methanol. Okay, so methanol attacks. Okay, so this was chiral, right? It was a R, this was the R isomer. So methanol attacks, and it could attack from in front of the board or behind the board. Okay, so we'll get a racemic mixture. Hydrogen is still attached. That. Plus, we'll get the enantiomer. All right, and then in the last step, another methanol will take this hydrogen. we'll get this ether plus its enantiomer. All right, so that's SN1. Okay, what about number 2? What class of substrate is that? Is it primary, secondary, or tertiary? No, it's primary. Yeah. See, this carbon, find the cursor here. Carbon number 1, the carbon with the bromide on it, is directly bonded to just one other carbon, so it's primary. Okay, so right away, that tells us it's not going to be SN1. Okay, it has to be SN2. Sodium iodide is a good nucleophile. That also is going to promote SN2. And DMSO was one of our aprotic solvents. So all of those things will favor SN2. Okay, so this one will be SN2. Okay, it's sodium iodide, but you don't have to do anything with the sodium. Just leave it out. It's a spectator. It's there to keep the charges balanced. Don't involve it in the mechanism at all. It doesn't do anything except, as I say, keep the charges balanced. All right, so iodide is going to come in from the back side, and at the same time, it will kick out the bromide. And so our product here will be the iodoalkane. Okay, I'm going to go ahead and erase this. All right, the next one. Okay, is that a primary, secondary, or tertiary substrate? It is a secondary, yes. Okay, secondary could go either way. Okay. CH3S minus. Good or poor nucleophile? What do you think? Okay, it has a negative charge. Okay, so that's a clue. Okay, CH3S minus is a good nucleophile. What about acetone? Is that a protic or aprotic solvent? Aprotic, okay. All right, so we got a secondary halide, a good nucleophile, aprotic solvent. So which mechanism is more likely? SN2 is more likely, yeah. All right. This time the leaving group is on a stereo center, a chiral center. Okay, so it's going back. Let's see, it's 1, 2, okay, so it's 5 carbons. All right, so there's a hydrogen coming forward. and our nucleophile is CH3S minus. Okay, and again, the sodium, just leave it alone, don't do anything. All right, so this is going to come in from behind the board. It will push the bromide forward. So our product it's going to kick the bromide out. It will push the hydrogen forward. Actually, no, I'm sorry. This comes in from in front of the board. And so that will be SCH3, and that's going to push the hydrogen back. Okay, so we start out, this is S. Bromine is 1, propyl is 2, methyl is 3, hydrogen is 4. But we're looking at it from the wrong direction. And our product will be R. Okay, this sulfur is 1, propyl is 2, methyl is 3, hydrogen is 4, so that's clockwise or R. So we get complete inversion of configuration. Okay, and then the last one, this is also a secondary. We've got a good nucleophile, we've got a protic solvent. Okay, this reaction will probably be slowed because we have this tert-butyl group in the equatorial position. So inverting the ring is going to create some steric problems with the tert-butyl group. Okay, that was substitution. Okay, that was substitution, and the other characteristic reaction of haloalkanes is elimination. And like substitution, there are two variations of elimination. Okay, whereas with substitution, you could get all kinds of different products. You could get a different halide, you could get an amine, you could get an alcohol, an ether, a sulfide, a thiol, get all those different products. With elimination, you're going to get an alkene. Okay, so we change the bond order. Substitution and elimination can compete with each other. Okay, so we can actually get both substitution and elimination products in the same reaction mixture. This is also called beta elimination because the carbon that's carrying the halogen is the alpha carbon, and then the next one over is the beta carbon. And the hydrogen on that carbon is called the beta hydrogen. Okay, and here the halide is again the leaving group. But instead of the O- bonding to a carbon, it bonds to a hydrogen, namely beta hydrogen, and we'll get an alkene. All right, this is important to remember. This is what's called Zaitsev's rule. Zaitsev was a Russian chemist, lived in the 1800s, same time as Mendeleev and Markovnikov. And according to Zaitsev's rule, the major product of a beta elimination is the more stable or more highly substituted alkene. Okay, when cis-trans isomerism is possible, the trans isomer is going to be favored. Okay, so in 2-bromo-2-methylbutane, we have two different sets of beta hydrogens. Okay, we have 3 hydrogens on this carbon here. We have 3 equivalent ones on this hydrogen here, and then we have 2 beta hydrogens here. Okay, so this is the alpha, the next one over is the beta. Okay, so that means we could form a double bond here, or this would be the same double bond if we formed it here, or we could form it here. So there's 2 products we could get. Okay, and we actually do get both products. The major product is this one, okay, because we have the most carbons attached to the alkene group, the most substituted. Okay, this one has 2 hydrogens and 2 carbons. This one has 3 carbons and 1 hydrogen. So this is our major product by Zaitsev's rule. Okay, another example here. This is 1-bromo-1-methyl-cyclopentane. Okay, so we have beta hydrogens on our methyl. We've got 2 here and 2 here. Okay, both of those sets of 2 would give us the same double bond. Okay, whether the double bond is here or here, it's the same product. And then the other one would be this external double bond. Okay, by Zaitsev's rule, this is the major product. Okay, like the one above it, this has 3 carbons and 1 hydrogen connected to the double bond, whereas this has 2 carbons and 2 hydrogens. Okay, so you're going to get both of these products, but you'll get more of this one. Okay, just like with substitution, there's 2 limiting mechanisms. There's the E1 and the E2. The E1 is one extreme. It's the breaking of the CX bond, and that's complete before the beta hydrogen is removed. And like the SN1, this is first order, it's unimolecular, that's where the 1 comes in. In the E2, okay, just like the SN2, everything happens all at once. Okay, so both the base and the alkyl halide are involved in the rate determining step, and it's second order. Okay. Okay, this is important information in the blue. It says only secondary, or in this case, tertiary carbocations are formed in E1 reactions. Okay, so if we have a primary halide, we can't do an E1. Okay, this is a tertiary, so it starts out just like an SN1. In fact, it competes with the SN1. So bromide leaves, we get a carbocation. We have 9 equivalent beta hydrogens here. And our solvent, they're using methanol, so solvent, the solvent will remove this beta hydrogen, and the pair of electrons in that CH bond are going to move here to form the double bond. Okay, so there's 2 steps in the E1. In the E2, everything happens at once. Okay, so here we have, we've got a strong base. It removes the beta hydrogen, we form the double bond, we kick out the halide all in one step. Zaitsev's rule also applies to the E2 mechanism. Okay, so how can we tell whether it is E1 or E2? Okay, well, if it's a primary halide, E1 will not occur because the carbocation is too unstable. Okay, so E2 is going to be favored. Okay, with the tertiary halide, E1 is favored. But you can have a E2 if you have a strong base. So with secondary, it depends on whether we have a strong or weak base. Actually, the same way with tertiary. Okay, so OH minus, OR minus are strong bases. So they're going to favor E2. Water and alcohols are weak bases, so they'll favor E1. Okay. Substitution versus elimination. Okay, I've been saying that these two compete with each other. The ratio of substitution to elimination products depends on the relative rates of these two reactions. Okay, which one is faster? Reactions with secondary and tertiary haloalkanes and polar product solvents give mixtures of substitution and elimination products. And so product ratios may be difficult to predict. Okay, it's considerably easier to predict the ratio of SN2 to E2 products. All right, the attack of a base on a beta hydrogen by E2 is only slightly affected by branching at the alpha carbon. So alkene formation is accelerated. SN2 attack of a nucleophile is impeded by branching at the alpha carbon. Okay, and we're just about out of time. A methyl substrate can undergo SN2. Why will it not undergo E2? Okay, why can't you do an E2 with say bromomethane? Okay, what is an E2 form? An alkene. Okay, can you have an alkene with only one carbon? Yeah, you can. Okay, so we're out of time, so I'm going to go ahead and stop here.